Hello, everyone. Thank you for joining us and be welcome to our webinar, Unlock PID Performance Insights with State-Based Analytics. I'm Vera from Control Station. I work in the marketing department, and I will be hosting this webinar with Bob Rice from Control Station and Tim Chope from Graphic Packaging today. And before we start, feel free to input your questions and comments anytime you want on the control panel here on GoToWebinar. There is a tab named questions and you can just type the questions there. And in the end of the webinar, Bob and Tim will be answering these questions. So our presenters are Bob Rice and Tim Chope. Bob has over 20 years of engineering and product management experience in the process industries. As a recognized leader, Bob oversees development of Control Station's award-winning suite of process diagnostic and optimizations technologies, including PlantESP control loop performance monitoring solution. And Tim is a highly experienced operations leader with a strong background in driving process improvements and leveraging technology to deliver long-term value. His experience as both a supplier and end users in our industry give him a unique perspective and insights. Tim is passionate about identifying opportunities across operations, processes, and control strategies to build resilient, future-proofed systems that generate sustained economic benefits. For those who are new to Control Station, we've been driving innovation in process control since the 80s, and today we are proud to support customers all around the world, including many of the leading manufacturers across the process industries. And Graphic Packaging is a fully integrated packaging company committed to delivering sustainable, eco-friendly solutions with a strong focus on innovation, graphic packaging designs, and produces fiber-based packaging that helps reduce environmental impact.
Excellent. Thank you so much for that introduction. Me and Tim are going to hop on here and we're going to get this the webinar started. And to kind of lay the groundwork for the topics, we're going to be focused on the challenges of kind of multi-state production and how do you deal with monitoring performance and optimizing systems that aren't in a single stage of operation. They run different products, different grades, they have different conditions, different states. And so we're going to talk a little bit about the challenges and the complexity and talk about some of the different types of applications to try to get you to think about your process is not this monolithic, singular piece of equipment that only runs one condition in one state. It's going to operate under a lot of different conditions, a lot of different behaviors. So we're going to talk through a little bit of those types of examples and talk a little bit about kind of the limitations of analytics when applied to systems that experience multiple states and multiple conditions. And so we're going to introduce the concept of state-based analytics. How do you account for these different conditions and these different behaviors when you're doing analytics and analysis of your process? And we'll talk about kind of the different types of tools and the different types of data that's required to actually, complete this type of analysis. We'll go through an example near the end and talk a little bit about a case study from the food and beverage space, and then try to kind of summarize the topics and have a Q&A, right? This is going to have we're going to try to kind of skirt some of the crazy math and try to talk in a little bit more in generalities around it. There are a couple of sections where we do get into it. I've tried my best to avoid it, but sometimes it's unavoidable. So before we get started, we're going to go ahead and run a survey question here just to help us understand the landscape, right? There's going to be a diverse amount of individuals in this webinar. And one of the things that me and Tim like to do is understand who we're talking to. What is the background in the industry that you represent? Are you from continuous manufacturing? Are you from batch manufacturing like pharmaceutical sites and so forth? Are you a system integrator where you're supporting a variety of different styles of systems? Are you an original, an OEM? We are actually creating the equipment, the skids, the systems that are deployed out there. Or are you from distribution, consulting, academia, or some other area? And we can use this to help kind of steer the conversation a little bit to kind of maybe cater towards those types of environments. And I know, you know, Tim, from your background, you've definitely bounced in, I think, all 4 of those, maybe even 5. I'm not sure if you've taught before, but you may actually be in all 5 of those buckets.
I don't know about teaching, but I've actually sat in and been a guest instructor a couple of times.
There you go. That counts close enough. And consulting and distribution. So
Yep.
you are in all 5 of those buckets. So I know you definitely bring a diverse background and experience, and it's going to be very interesting during this webinar to kind of hear some of your stories and war wounds about applying analytics and understanding processes that kind of move through those different states.
Yeah, looking forward to it today.
Yeah, let me
Excellent.
show you the results.
Yeah, let's see, what do we got here? All right, so a split between other and continuous, which I'm assuming probably on the distribution and consulting side, maybe on the heavier side, continuous, system integrators. Good. Excellent, excellent.
Let's come back to the slides.
So, you know, Tim, what are some of the challenges and so forth we have when we're dealing with kind of multi-state production?
Well, I think if you start looking at, you know, whether you're talking about batch or continuous, there are different states or phases that you go through, right? Whether it's a batch where you're loading a vessel, steaming a vessel, whether there's an exothermic reaction going on in that vessel, you know, how each and every one of those loops behave during those different phases can be drastically different. In a lot of cases, you may use the gas off valve for both temperature and pressure control, right? You may be trying to maintain temperature in a vessel with a exothermic reaction, and at the same time you're kind of overriding that with don't let the pressure get too high. So I think it's very, very important to understand those states or those phases as you're looking at variability of a given control loop. And you know, sometimes in a batch process you don't really care, you know, how that 400 gallons of chemical got in that vessel, you know, what the variability was when it went in. And other times you're ratioing it with another ingredient or raw material that you need to maintain that ratio and need some stability as you're loading or steaming the vessel or whatever the case may be. So it's very important to understand the process and then understand, do I care about the variability during this phase of the process, or is it during the next phase or the final phases where I really care about the variability? And then, you know, if you have part of a process that's continuous and part of a process that's batched, right? How do you campaign that batch so that you don't disturb the raw materials into the continuous process, whether that's upstream or downstream of that process? So it's, you know, and even at that can be, you know, what is the demand base? Or are we running at 100% of capacity today, or 50% of capacity due to market conditions, et cetera? You know, what does that do to your turndown ratio across your facility? I think understanding all of that gives you some line of sight as to where you need to address it.
Yeah, I mean, there's so many, you know, challenges, especially when you start to combine batch and continuous systems and all the different states, all the different product grades, all the different rates. You know, again, see, systems are not these monolithic creatures that sometimes when you are trying to take a simplistic view, you try to treat it as, oh, it's just one temperature controller, or Tim's again, one pressure loop, and that's all I care about. Well, no, I may care about that pressure loop different ways depending on if I'm in startup, I'm feeding the system, and I'm in a final exothermic reaction, whatever it is. Not only does the control say objective change, but the analytics and the metrics, the KPIs, what you care about may actually change as you move through, and it becomes a very challenging problem to actually ascertain. Can you go ahead, next slide, Vera? And you know what's kind of interesting is, you know, these, you know, multi-state production processes don't just you know, show up in pharmaceutical, right? Because that's probably where most people would say, oh, well, batch, and it only applies to us in the pharmaceutical industry because we've got batching and reactions and stuff like that. It's everywhere, right? In chemicals, in power generation, in pulp and paper, in food and beverage. everything is always changing, right? Startup and runtime versus shutdown is probably the simplest types of states, but those are very different control objectives that you're going to have to deal with in all of these spaces. In food and beverage, in pulp and paper, you run different grades, different products. Your machine may be running completely different specs from A to B, and you're expecting that same piece of equipment to do the same thing, right? It's like, you know, you've got a car, and some weekends you're on a race, and the other you're driving back roads, and some you're four-wheeling, and you're expecting this one little vehicle to handle all of these different conditions. It can be a bit challenging, and it's not just in one particular industry. Even in power generation, right? You've got plants that are not necessarily designed to run at one specific load. They could run at full load, half load, and now you've got peaker plants that have to come up and down and move around, and all those are very different types of productions and states. And you got to start to realize all of these actually do have, you know, a lot of different conditions in there. And, you know, I'm going to let Tim speak about pulp and paper because, you know, that's a big part of your history there, and the states and conditions there, they're crazy.
Yes, they definitely are. And as I mentioned earlier, you may have batch digesters, you may have a coater kitchen that's making batches. And how do you maintain a stable supply for the upstream and downstream processes through that batch process? The other thing that, you know, has to be taken into account is what's your production rate doing, right? Are you stably running, or are you campaigning really, really rapidly, then you run to failure, and then you're down for 3 or 4 hours? And what does that do? And how do you leverage the attenuation in different storage chests or tanks to offset some of that variability transitioning from one unit operations to the next operations? You really got to look at, even though you're concerned with individual control loops, you got to understand that it's a holistic ontology of how a site or a facility runs that makes that happen. And back to power generation, right? We're in the hours, you got energy consumption all over the place, and load shedding can be a very, very important part of, how do I step a facility down to protect the surrounding area from a power outage, so that everybody can stay cool, and do that in a uniform manner that doesn't disrupt my process for the next 3 days, trying to get the recost or liquor cycle back stable inside a facility. It's all these different transitions. You have to understand, when do I need a loop to be aggressive, and when do I need a loop to have some resiliency, right? Whether that it's demand based or disturbance based rejection that you're trying to make a loop operate under. And that's just, I don't care what process you're running, whether it's a refinery, a chemical process, or pulp and paper, you're going to run into transitions over and over again.
Mm-hmm. Yeah, and with, when you deal with a lot of different sources of complexity, depending on the type of industry, right? Nonlinear transitions, cycle times, as you kind of talked about, how you actually want your plant to operate. Do you need it to be very quick to recover from loads very, very aggressively so you don't lose control, or do you need to be much more stable in your process? And you've got these asynchronous events that don't occur, on a timely basis. It can be a completely unknown source of variability, and it's just an incredibly complicated scenario, right? You think about, again, not just the control objective that we're trying to try to document, the control narrative. It's going to be this multi-dimensional challenge, right? Control loops are not as easy as they make them look in the textbooks, right? There's a lot of different variability associated with them. That complexity can come from a lot of different areas. Can you flip to the next slide there, Vera? So we think about the challenges, right? And it's the impact on plant performance. And me and Tim have kind of alluded to this. All of this variability, all these different states, all these different conditions drive all different types of analytics and problems that are associated with the plant. And some of these changes can actually impact the variability of the plant. You talk about the economic factors, right? Energy, quality, and output, right? In a power plant, it's how much energy do they need to produce? Am I at full load, half load? Am I chasing that load to be able to maintain stability to the grid? Am I maintaining specific quality? And sometimes you actually are trying to produce a lower quality product because that's what you have probably the most demand for at the time, right? You may be chasing output, right? You may need to run a lower output or a higher output depending on what you're trying to do. And you're trying to, adjust those characteristics to run the unit to gain the most economic advantage, right? It's not always running the most expensive product. You may want to run different grades of products because there's more demand in the marketplace. So now you got to shift production to that, right? And so moving those production limits is going to impact plant performance, right? Human factors, who's operating the board, right? Whether it's Billy or John or Megan or whoever it is who's running the board, right? They may run that plant differently. That's going to potentially impact performance. It could increase alarms. It could have safety issues attached to it, right? Reliability, right? I know, Tim, you've got a lot of experience around kind of the instrumentation side and understanding the impact of reliability of the equipment and how that impacts the conditions and states and wears and tears, and whether you've got the right spares and downtime and you've scheduled those events. From the impact of kind of plant performance, from the instrumentation side, what do you see as some of the biggest challenges?
I think if you look at, the history of advanced control over the past, 30, 40 years, right? Model-based predictive control has been a thing for a while. And every one of those are very productive when you first put them on, right? I mean, you can drive energy cost out, raw material utilization, you can drive variability out, whatever your cost for production, you can increase yield and decrease cost with those. But over a period of time, 3 months, 6 months, whatever, that model will apparently drift. And the pipes don't get bigger, the pumps don't get bigger. Something is changing underneath it. And quite honestly, in many cases, it can be instrumentation issues, right? Whether it's wear and tear on a pH probe, a little buildup inside of Coriolis tubes, whatever the case may be. And I think very, very often the first thing we do is let's go retune a loop, or let's go rebuild a model, as opposed to let's go look at the field devices that are out there, whether it's a final element from a control valve or instrumentation on the front end. Math doesn't change, right? We've been playing with the same math for a very, very long time, and those rules are pretty much fixed at this point. So the only thing that really can affect it is the inputs and outputs. All right, so if you have a instrument that maybe got recaled or respanned, I've gone to, I don't know how many places that you go to an instrument and you hook up a heart communicator to it and it spans 0 to 200, and you go get in the DCS and it spans 0 to 100, right? I mean, every time you go respan one of those things, you have essentially changed the gain of a loop. Same thing with people putting time constants in as transmitters become more and more intelligent. The ability to go put a 5-second time constant filter in an instrument that is unaccounted for in the control loop strategy, or vice versa, right? They don't put any dampening or attenuation in the instrument, and you have to filter it in the control loop so that you're not inducing fold over frequencies or things that you can't control. So I think we have to start looking at the whole thing holistically. And I know that can seem monumental, but I think that the one thing that gives me hope in today's world is the advance in computing power, the investment in the availability of, whether it's machine learning, AI, etc. If you think about simple things in our lives today, right? Whether it's, as we were talking earlier about Alexa and Siri and everybody listening, but just try and outrun Google Maps today, right? 10 years ago, it would say you're going to be somewhere at 8:30, and it was a race. You could beat it. You could get there at 8:10. Today, the number of sensors, the number of inputs, the math that's behind that, it's looking at wrecks up ahead, it's looking at traffic jams up ahead, it's looking at, there was a sudden downpour and all these iPhones slowed down. So, I think the ability for us to do analytics in a state-based environment is going to become easier, less complex, because we're going to have horsepower to help us do that in the not too distant future.
Yeah, it becomes this kind of multi-dimensional problem, right? Where it's not just you're looking at one number and tracking it. It's that one number, how it's being influenced by all these different factors, right? Those are the kind of states and conditions. And you got to think through what are the performance metrics? What are the KPIs? What are the values that we're trying to get? And what role and influence do those have on these other factors, on the economic factors? Those can drive the KPIs and KPIs can drive it. It's this very complicated problem, and we are going to start to try to narrow down into a solution. The idea here is to try to understand how grand this is. And I will say, we're not going to solve this problem in 25 minutes, right? This is a very kind of larger kind of thought process around understanding states and conditions and how do those impact production. And a lot of it is about kind of understanding controller performance and how do you baseline that. If you want to flip to the next slide, Vera, in our next webinar, because again, I told you we can't tackle all of this in one webinar, right? We've tried to kind of break up and talk about different pieces, is to, when we think about controller performance, not just state-based but others, we have to understand, what does good control mean? What are different KPIs? What are the numbers that we can use to actually track the performance? And in our next webinar, George Buckby is actually going to go through with us and talk a little bit about overall controller effectiveness, how we can use that as a KPI and a baseline and a benchmark to track controller performance, and what impact do those have on the economic factors, the reliability factors, the human factors, and how do those impact OCE and back and forth, and how do you actually baseline determine what is good control? How do you layer on, you know, the thresholds for where you consider to be good and bad, right? You can have a number, but unless you actually understand what that number is relative to targets, you don't know if you're in a good shape or in a bad shape. So George is going to spend some time kind of talking through some of the practical approaches, different ways to interpret the numbers, to baseline it, talk about established benchmarks and individual site benchmarks. And, you know, George is an excellent speaker, and it's going to be a great one. I'm really looking forward to this one. That's going to be in August. So before we get into the deeper math section, I suppose, one more survey, right? We want to talk a little bit about your current approach to PID tuning issues, right? We've talked about a little bit of the challenges associated with it, but now how do you actually go and identify the opportunities, right? Are you using automated monitoring tools? Are you staring at trends and waiting on operator feedback? Do you do annual or periodic style performance reviews or audits? Are you being kind of purely reactive to wherever the problem comes in, I go and do it? Or, you know, you don't really have an approach. You just go out and you do it, right? You know, automated monitoring and the manual trend analysis tends to be probably the most common, especially with a lot of the powerful analytics tools out there, whether it's PlantESP for loop monitoring, or, you know, quite frankly, even doing things within Excel and being able to track the data is actually a really important way of just, you know, trying to facilitate a way to make it automated, right? How can we actually, you know, have an approach that is not reactive, hopefully? I mean, I'm assuming there's going to be some people who are purely reactive, but how do we move people towards a more automated approach using all of this intelligence and data and analytics and so forth? So how we doing, Vera? Are we getting to a quorum on the results?
I will just 5 seconds more and I will close and share the results.
Very good.
Okay.
Yeah. Manual trend analysis and operator feedback. That's not a surprise, is it, Tim? Right?
It is not.
Wait for the operator to tell us that there's a problem and we're looking at trends, right?
Yep.
Yeah, that's yeah. Hey, but you know what? Second is automated monitoring and analysis. So there is a little ray of sunshine in there that, you know, we are making that kind of progress in there. And so as we talk about controller performance, yeah, it's encouraging. So you know, Tim, when we think about controller performance, what are the kind of different aspects around control that you know you look for identifying controller performance, and what do you think about and look at?
Well, I mean, certainly, you know, probably the number one thing you look at is set point versus PV, right? You know, what's the 2 sigma or the COV or the variance of that process variable. The others are, you know, what am I having to do to a control valve or variable speed drive or whatever the final element is underneath that to try and maintain that low 2 sigma or low COV. And, from there, I also many times go look upstream to see what could be inducing that amount of variability that's making me have to drive that actuator that hard to maintain it. A lot of times, people try to control levels in tanks or chests tighter than actually the tank or chest was designed to do, which means you create a demand on an upstream or downstream process because you're inducing so much effort trying to maintain a level in a chest when it is really there to absorb and attenuate pulsations, and it should be allowed to ebb and flow so that you don't put demand on the upstream processes. Very often, back to the paper industry, a lot of times when we are in a startup condition, we will start a machine up at a much slower rate than it normally will run. And so that ramp up curve to get to its normal production rate places a tremendous demand on the high D chest and the pulp mill upstream of it, right? So if you pull on that too hard or too fast, you will induce cascaded frequencies all the way back to the originating source. So, that's one of the things I always try to look at is, how much effort am I having to put into that control loop or that final element to maintain the 2 sigma variability that I'm looking for? And then is that 2 sigma variability correct, right? Am I driving disturbances external to that loop by trying to control that loop tighter than it was originally designed to do? I think one of the things that we overlook a lot of times is control loop utilization. We can look at all the metrics we want to around, how well is it maintaining set point, how quickly is it getting set point. But by and large, if an operator is not using a loop, there's a reason, right? I mean, it's doing something that they don't either understand why it's doing it, or it's doing something that it shouldn't be doing and it could be during a certain state or phase or condition of the process. It may work perfectly fine every time that it's in a steady state running condition, but getting to that may be inducing variability everywhere else. So, never be afraid to go ask operations, go sit down with them and figure out, why did you put this loop in manual? Why is it always in manual? Don't be afraid to walk out in the field, right? I can't tell you early in my career how many times I got kicked in the teeth because I didn't go look at the field and understand that there was a split range out there in a 4 to 20 that I didn't have any line of sight to in the code and the controller, etc. And tune it for a certain demand base, and then suddenly something happens in the process, it kicks into the next valve that you didn't know it was there, and you've completely lost control of the loop. So, if your control loops are not being utilized, there's something wrong. I'm a big believer in, people will take advantage of any technology that works, and they will avoid anything that doesn't work. And that kind of gets me to the behavior thing, right? Are those KPIs and metrics and things that you are placing on these, are they driving the right behaviors and the right responses that you want, right? If you have applied an advanced control or advanced control strategy, doesn't even have to be APC, MPC, any of that stuff. It can be a complex cascaded PID strategy. If it's not doing the right thing, don't force utilization on it, because the operators 9 times out of 10 will show you that it's not doing the right thing. You need to tie those KPIs and metrics back to, variability reduction, energy cost reduction, raw material cost reduction. Don't put it on, this loop has to be on control 100% of the time, because trust me, if it's doing what it's designed to do, the operators will use it. So
yeah, and it's all of these kind of factors kind of play into the mindset. And again, as kind of Tim went through, everyone kind of approaches this. When you go and look at controller performance, it's how your mind works. It's is it an automatic? Is the output moving too much? Is the variance acceptable for it? But there's challenges with this. If we go to the next slide, the challenge is a lot of times when you're looking at controller behavior, you're looking at metrics, you're looking at from an aggregated view. Hey, what is the percentage of time the controller was in automatic over the last month? Okay, it was 95%. Pat yourself on the back, that's great. But what about that 5%? what is attributed to that 5%? You go back to kind of Tim's comment of, well, when the operator is running in startup, they always put it in manual, right? So if you start to take those KPIs and you start to, instead of aggregating them for just an entire monthly average, but kind of break them into the different conditions and states, you can start to actually uncover what the actual problem is. You know, you may be saying, well, 95% is pretty amazing, except when you go and say, oh, when I'm in startup, I'm running 0% of the time in automatic. Okay, well, that means every startup is not as good as it could be because the automation isn't there, right? And then you have to go into, okay, is that operator behavior? Because that's the way they've always been trained. They don't even know that the controller can run an automatic during startup, right? So when you aggregate, you collapse everything down to a single number, you start to lose some of the context and kind of data and around that particular number, right? And if you're just looking at a single aggregated view, you can't really distinguish all the individual states that make up that particular data. Are you running different grades? Are you running different conditions? Are you running different board operators? All of these things can influence the KPIs. And if you collapse them all down and look at a single number, well, you're gonna have flawed diagnostics, or you're not gonna be able to uncover the real challenge with it, right?
Yeah.
And so when you're looking at traditional data, you'll lose the context, right? And so the need for state-based analytics is really important.
I think the one thing I would add to that, Bob, is, you know, even getting in the shower, right? When you first turn the shower on, you throw that valve all the way to the hot, and then you start backing it off. You do more adjustment to that valve in the initial phases of getting the shower warm and getting in there than you do the rest of the time you're in the shower, right? I mean, that's kind of steady state. Once you get to a steady state, you can turn most PID loops off, right? At steady state, if they're self-regulating processes, you could turn the loop back into manual. The critical states are the ones that they're not using it.
Mm-hmm. Yeah. If everything stayed perfectly steady, you don't need a PID. You need the PID for when you actually have all the variability, because a controller can react quicker and better than an operator can, because they're making decisions, you know, every 100 milliseconds, every second. Whereas an operator, you know, maybe if they've been doing it for 20, 30 years, they know, just like I know in my shower, I'm going to put this knob exactly here when I start, and I can turn it and I can make the 3 adjustments. But I know, Tim, with you, you're in traveling a lot. So when you go to the hotel, you know, every hotel is just a little bit different, and you have to play with that knob, right? And you know,
Yep.
again, so many analogies here. We love analogies in process control, right? But the idea here is there are challenges, right? And you have to understand that your process is varying conditions. And so if you take this kind of monolithic approach to metrics and just say, okay, over the last month, this is what it is, you may get a number that's good for maybe corporate baselining. But if you're actually trying to do diagnostics and determine, well, why is that 5% there, right? You have to kind of expand that data to be able to ask yourself better questions. And so if we go to the next slide, you know, this kind of introduces what are some of the questions, you know, Tim, that you would go through and kind of ask yourself from a state-based analytics standpoint.
Yeah, I think, you know, I think we've touched on a lot of these already, but, you know, where are we at in the state? During that state, do I care about the demand on that loop, or do I care about the disturbance rejection? Am I in a startup condition, which is going to rapidly change set points, as opposed to once I get to a steady state and I'm relying on the process to absorb a lot of the variability on its own? You know, and as we mentioned earlier around batch processes, right? As that batch process is feeding a downstream continuous process, you know, how do I ensure that I'm campaigning at a rate that I can support and sustain both the supply and the downstream processes around it? And so you really have to break it down and look at everything in the individual components, and then roll it up to, are my metrics and what I'm trying to do with this holistically. You know, a lot of times from an APC standpoint, you may not want that APC on control during a startup condition. It may be very, very good at maintaining steady state or disturbance rejection, but it may not be very good at demand based. It may not be ideal for, I want to get to my production curve quicker or faster, or you may tune it for that, and it may induce variability when you're at a steady state. So you need to look at all the different states that your process can run, and it's not always just states, but it can be conditions, right? And back to the paper paper mill analogy, you may have 2 or 3 machines in that facility that are consuming pulp from the pulp mill. And if one of them is down for an outage or a turnaround, the demand placed on the upstream processes can be very different. So, you just got to be very aware of the demands and the processes around you.
Yeah, it's really about trying to, understand what are the challenge, what are the states, the conditions that we care about, right? How do we actually extract out, is APC on or off? How does that influence it? Is it a process sequence? Is it a load of the plant? Is it a product grade? Is it a batch sequence? Is it a startup condition? What are the things that are driving those behaviors? And if we go to the next slide, I need to do a little bit of definition because we have to kind of talk about terminology a little bit. We have this kind of idea of state-based analytics, but we haven't really defined conditions and states. We kind of use this word, and I think everyone's got a kind of a rough idea of kind of conditions and states. But a state is kind of a unique combination of conditions. A state isn't just one thing. It's kind of a unique combination of different conditions that you have. And so if we kind of look at an example here, let's say we've got a PID controller, and it can be an auto, manual, or cascade, right? That is a set of conditions that the controller can be in, right? I've got an APC system that can be on or off. That's another condition of the system, right? Now I've got a grade list where I'm running grade A, grade C, or grade X, or whatever it is. That's another set of conditions. A state is a combination of those conditions. So a state would be, I'm in automatic while APC is on and I'm running grade C. That is a state, right? And so you can think of kind of about your process. A process can have lots of different condition lists. Each of those conditions can be operating. You generally are only operating in one condition from each list at a time. It's not like I'm running grade A and C simultaneously, right? That is a unique condition. But a state can be any combination of those conditions. And you're going to see later on as we start to kind of go through an example of an analysis why this definition helps us kind of do our analytics, because it allows us to kind of group our data or bundle our data into sections or into states, right? So we can say, look, I want to understand the behavior or the context of my data in the state in which I'm in automatic, APC is on, and I'm running grade C, versus a different state, which is I'm automatic, APC on, and I'm running grade A. So I have two different states that I can now compare it, and I've kind of defined it. And I can combine those states to create any kind of context around the data. And you could add more condition lists. One of my favorite ones, I haven't had a customer willing to do this yet because I think it caused me issues, is run the board operator through, right? What shift or what board operator is running the unit as a time, and now use that as a state. So when I'm running, when Billy's running the board versus Johnny, right? What are the KPIs and behaviors of my facility based off of that state? Because that is a condition of the process, right? And all of this really allows us to kind of expand out our kind of thought process for how we want to group analytics. And analytics themselves, if we start to improve them, we start to get better performance, right? That's where we get the value, right? And if we go to the next slide, Tim's going to talk a little bit about kind of the value. If you go and work towards controller optimization, we're not doing this out of the goodness of our hearts. That's because we love tuning PID controllers, right? Well, maybe I do, right? But Tim's got a real job. So he's got to actually follow the numbers, right? And so when you do process optimization, Tim, what are the benefits that you generally start to see when you put some effort towards this?
I think it's, in a lot of ways, it's kind of across the board, but the biggest thing is that if you can increase production or reduce energy consumption or raw material cost, it's unbelievable. If you look at a facility that runs, 24 hours a day, 350 days a year, just increasing yield of a unit operations, a tenth or a 1/4% in a large facility is huge economic windfalls, right? I mean, so it depends on the type of loop or what you're looking at, whether you're definitely looking at production throughput or reduction in quality variables, etc., you have to look at the economic conditions of your process, right? If your machine or your process is 100% booked out or your order book is full, right, then producing more product doesn't really help you, right? As well as you could be completely full and running production. If you can save 4 or 5% of energy consumption, then that cost is unbelievable return as well. So you got to take the economic conditions, the industry conditions. You know, I've seen things swing based on even some byproducts, right? You know, in the paper industry, you know, there are a number of byproducts that are made, turpentine, etc., that depending on the pricing or the market for that byproduct, there may be times that you don't want to generate a lot of it because it's not really worth your time, energy, and effort to handle it. And then if the price goes up, you may want to change how your process acts and behaves to create more byproduct. So, you know, that there are general rules of thumb, and then there are varying and changing economic conditions within an industry. You know, and I think every industry goes and follows that, right? Whether you're in oil and gas, food and bev, et cetera, everybody has economic drivers that change. And it's sometimes it's very enlightening to see how different markets can affect your market, whether it's, you know, increased housing can drive the cost of caustic up in a paper mill because of PVC pipe being built and consumed by building houses. It's really, when you start looking at the macroeconomics, it's really interesting to see how industry changes can impact your economic benefits and where you need to focus.
It's, you know, it's really about that, you know, they keep moving the cheese on you, which is the KPI, which is the economic factor that you're after. Is it more production? No, it's actually not more production. It's less production, but with less energy, right? Or using less caustic or less raw material, or using this side grade material over here. But, you know, the value of improving control is kind of easy to start to quantify once you start looking at production rates and energy consumption and so forth. And
one of the things that control does give you is the opportunity to be agile in those approaches, right? As the economic conditions change, you know, how can you pivot your unit operations or your facility to take advantage of those as opposed to being penalized by them?
Precisely. So let's go ahead, and I'm going to go through kind of a quick example. Me and Tim are going to talk about kind of an example. This is from an edible oils facility. This is a bleaching process, and a bleaching process is used in kind of oilseed refining, and it's a critical step for essentially kind of improving the color, purity, stability of those. And it's a very kind of important process. It's got a lot of different control loops. It's got a lot of different kind of aspects attached to it. And so it's a complicated process. It's a lot of different states, it's a lot of different conditions, right? It's not just running one product grade, it's going to run multiple product grades. This system also had an APC system applied to it, where sometimes the APC system was running, other times it wasn't, right? There's also opportunities where maybe control loops were not being utilized as they should. Some were in auto and some were in manual. And there's a primary kind of temperature controller on this at the tail end. That's just one part of this. And what I wanted to do, and what we wanted to talk through, is kind of an example, is just kind of taking that kind of micro look at this one controller and trying to understand all the different aspects of the states and conditions of this process that influence it. If we just look at kind of an aggregated value, you don't get the full picture. You need to expand it out a little bit. And so if we go to the next slide here, right, it's trying to understand the process, you know, and if you look at this, there's a lot of different states and conditions. And Tim, if you want to kind of walk us through a little bit of just what you see on the trend.
Yeah, so on the trend, and it is a bit of an eye chart, but you can see that there's a definitely change in controller output, right? So something is changing demand of controller output. That could be pH of the product. That could be, every bleaching application has a bleaching curve, right? At the top end of that curve, there's diminishing returns on adding more chemical to bleach. you don't get the same bleaching impact at the high end of the curve that you do in the sweet spot of the curve. So, you know, whether that is production rate that's impacting it, temperature, pH of the raw material, you know, color of the raw material that's coming in that you're bleaching, all those disturbance variables are interacting with one another, and you see a lot of different changes here of a lot of output changes as well as demand-based changes.
Yeah,
And
there's a
again,
lot of things going on.
yes, and then when you put an APC over the top of that, then you're looking at this loop. Is it, you know, now it's being asked to respond to set point changes rapidly, as opposed to previously it may have been running to one set point and just rejecting demand-based issues or disturbance-based issues. And so how you tune and how a PID responds to that is very different.
Mhm. If we go to the next slide, right, we'll try to maybe even expand some of the context of this, right? It's an eye chart, and it's designed to kind of show you, if you're just looking at trends, man, God help you, right? You're just trying to, you know, try to pull apart all this data in your head. And while our brains are very good at this, there's a lot of different states and conditions, right? There are 9 different kind of combinations, right? The first 2 trends are basically your simple PID, but then you've got, am I an automatic or manual? You've got APC on and off, and you've got product grades. In this case, there's just 2 of them, A and C, that kind of toggles through. And this is, you know, 160 days of data. It's a fairly wide range, but you can see the condition of the APC does flip on and off. The mode changes, the states of the grades, all this stuff changes all of the time. And if we try to collapse it into a single value, we're not going to get a lot of information out of it. If we go to the next slide, I'm just going to kind of show you the answer, right? Because that's what everybody's here for. And this is kind of the example of understanding states and conditions and how you can expand along kind of different states. If we look at the results at the very beginning at the top there, if we collapse everything, say, look, over the last 160 days, the variability of our temperature controller is typically around 3.1 degrees away from the temperature, right? So we have an average error of about 3.1, and that's higher than what their threshold should be, right? What does that tell us? Not a whole lot, right? Other than, hey, over the last 161 days on average across all the different conditions, we ran some higher variability. But what was the actual kind of state or condition that caused that, right? So we can do some exploratory study. Well, let's just think about it, you know, in state of, okay, I'm in automatic. What about the different grades? Is there a different behavior between grade C and grade A? So we can expand along grade. We can say, okay, look, yeah, grade C is slightly higher variability than grade A. Well, that's interesting, right? Why is grade C worse than grade A? Now let's take about, well, what about impact of APC, right? Well, this should make all the APC fans happy, right? Because, hey, when we turned APC off, guess what? Our variability jumped up to about 5 degrees on this temperature controller versus APC on, we're down to 2.2, but we're still slightly above where our design spec was. When we take it to a fully expanded and we really start to see the context behind that KPI across the different conditions and states, we can start to see, aha, when I'm in APC is on and I'm running grade A, I am spot on perfect. I've got my below 2 degree variability on this temperature controller. It's doing exactly what I need to. But when APC is on and I'm running grade C, my variability is higher. Why is that? Well, in this particular scenario, it's because the APC system wasn't designed or calibrated and modeled for grade C, it was for grade A, right? And so all the models, how the behavior of the system is under grade A is different than grade C. So the APC system needs to be modified to be able to support that variability. So now we have a clear idea of what we're doing because we didn't treat the data as a monolithic system that's just, hey, look at this. Let's use it as a troubleshooting standpoint to identify the actual point and the problem and the state and the condition that we need to go do. Let's actually have some actionable information versus just a singular number that we're tracking as a function of time. So it's adding context to the data. Okay. And I knew this was going to happen, Tim, but we've definitely run a little bit long, but we've timed it just perfectly so we can get to the summarizing and the Q&A slide here. You know, we've covered some of the state-based analytics. kind of going through poor regulatory control, kind of the ways that we can use state-based analytics. You know, any kind of parting thoughts before we get into the Q&A section, Tim?
No, I think it's been a great conversation, and I'm looking forward to the questions.
Excellent, excellent.
Before the questions, I will just run another poll. It's more a contact information, so sorry, I don't know what happened here. Oh, well, let's start with the questions, and I will try to fix the poll here. So what type of information and data is needed in order to operate state-based analytics?
Lots of data, right? You need to have that context, those states historized somewhere, right? You need to know, am I running grade A? Am I grading grade B? Is APC on? Is APC off? Is Billy or John running the board? Is the, you know, states and conditions, and we talked about this, I think last week or so, Tim, was, you know, environmental conditions. What's the outside temperature, right? Are you operating in summer versus winter? I don't know how many loops I've worked like, oh yeah, in the summer this thing doesn't work, but it works great in winter, or vice versa, right? So it's having that type of data. Is there, you know, Tim, from your standpoint, are there other thoughts, or what other kind of data you think is relevant for state-based?
I would definitely start with simple, right? You know, if you look at state-based alarm analysis, right, you don't want to alarm a pressure when the pump isn't running, or a flow when the pump isn't running, or when a flow is below X%, right? Don't alarm off of it. So there's many simple things you could do either in PID loop health monitoring, or even if you're pulling it into Excel, right? Just basic things is this unit operation up and running? And should I be doing analysis on it right now? So you take all that variability and all that disturbance out of there, because, you know, with a Mac flow meter, if you've not done something to state-based that instrument, you're going to get empty tube readings, right? It's going to read all over the place, which is going to show you variability that doesn't exist because there's either the tube's not full or the process isn't running. So I think just the very simple things, you know, almost tying it to alarm, the very beginning of alarm rationalization, right? Is my process not running, or am I shut down and I need to suppress all this analysis during this time frame?
Okay, excellent. Next, is there another question out there for us, Vera?
There is, how does state-based analytics tie into other modern technologies and like AI and machine learning?
Oh, that's a good one. Tim, you want to talk a little bit about how state-based ties into machine learning and AI?
I think AI or machine learning is very, very good at figuring out what interacts with what, right? But at some point, I think you still got to rely on a little bit of domain expertise or SME looking at that model to discern the difference between causational and consequential, and just, you know, a door opening didn't have anything to do with the flow going through the pipe at that particular time, right? There's at some point you still got to apply some domain expertise, but I think it's going to be very, very good. You know, I mentioned, you know, Google Maps and it being able to ascertain that there's a traffic jam up here and predict how long it's going to take for you to get through that. I think that anomaly detection is going to be very good at saying you're outside of a normal state. Here's a state and a condition that I found. Do you want to pursue some analysis in that environment? And a lot of times it may be states or conditions that we're not even, you know, acutely attuned to, just like you mentioned, the external influences, right? How you control a cooling tower when it's 102 degrees outside is very different than, or what the demand is on a cooling tower is very different than when it's 80 degrees and raining outside, or even lower. So I think, you know, as we start bringing more and more data into these models or into technology that can help us find the interactions, we're going to be shocked and surprised to see some of that. I know many years ago, I was using some tools that could do some principal component analysis and look at a process holistically, and it could break down out of 300 different process variables that were coming into this PLS model. It could break it down and say, okay, you deviated by X% of confidence factor on this model, and this is the process variable that induced it. And it was really interesting to find positive and negative correlations and things that I never really thought of could be affecting stuff. It can open your eyes.
Yeah, the conditions and states applied to those become the context to which those models operate too, right? So if you've got a machine learning algorithm, how it operates when you're running different grades, different products, different conditions becomes actually another input to those AI models, because it's not just the temperature of the unit or the PVs of the unit, it's the context to which that plant is operating becomes more and more knowledge, right? If you start thinking about what a super operator is capable of, they're capable of understanding the process because they take in all these external state-based conditional data almost naturally. They know it's summer, right? So it's operating a lot hotter than what it does in January, right? They may know the different product grades. They may know they're running under higher load or lower load or demand, or they're chasing this or chasing that, right? They've got all these different states and conditions, and that influences the decisions that they make. When we start to look at things like ML, clustering algorithms, AI, modeling algorithms, stuff like that, those inputs have to be applied to those, because otherwise you end up with this aggregated AI model that's not going to be as accurate, because it's going to start telling you things that don't make sense, right? Because you're taking data from 365 days, and well, half of it's freezing and half of it's warm, and you can't put those two data sets together. You have to start to partition and condition the data to cluster it with the states and conditions. So all of these ideas have to be kind of added to the historian, added to context, right? These kind of abilities to capture these states. And it goes back to our first thing is, the more of those states and conditions you can start to historize, even if you're just visually looking at the data, sometimes it's useful to say, hey, oh yeah, look at that. The last 3 weeks, it's been 105 degrees outside and everything was terrible, right? You may not know that, the operator may, because they may be used to it for the last 15 years. So it's these conditions and states should be treated like an input to the models like anything else. So, and I know we're going over time here, Vera, so.
Yeah, so last question, how do you account for different PID tunings across different states? And while you are answering that, I will just share here the contact information for those who want to contact us. Make your another questions you can send us through our website.
Okay. Yeah, I mean, varying tunings are a state, right? I mean, you're changing a conditional parameter around it, so you could treat it as a different state. So as an input to the model, you could say I'm using aggressive tunings or conservative tunings, and that becomes part of that kind of analytics, right? It kind of just depends on how different the tunings are, what your control objective is. But anytime you are changing something about the objective of the process, right? That was something Tim had mentioned earlier. You've got different control objectives attached for the process, right? Sometimes you care about fast control, sometimes slow control. You can't compare apples and oranges because the KPIs, the controller performance, the objectives of those could be different, right? And you may need to actually treat that as a state, separate the analysis and treat it as a state condition. And you probably don't want to do it if you're doing like gain scheduling where there's an infinite number of gains between A and B. You may try to put them into buckets and say, look, if I'm between these two parameters, I'm in an aggressive, and these two parameters, I'm a conservative. But a lot of it just also depends on, Tim had said earlier, keep things simple. It depends on how complicated, how important, how much economic value there is to solving the problem, right? I love data. Give me more and more data. I'm all for it. If you need to solve the problem, generally you need a very small amount of data to get 85% of the answer, right? But that last 15% of the answer, that's the expensive part. And you may get a decent value from it, but it's still a lot of work to get the last bit. So yes, you could treat it as a state, but you have to ask yourself, is it actually significant enough of value enough to do that, right? It's the same reason we could put adaptive control on every single PID loop that we have in the plant, but we probably don't need to do that because the value of the return isn't necessarily there for it. So you kind of have to do that little bit of that calculus to determine is the value there before you start applying a bunch of additional states and conditions and so forth to your system. So excellent.
That was really great. Thank you very much, Bob and team. It was a great session. I hope you all enjoyed the content here. And as I said, feel free to reach us for your questions, everything. And go to our next webinar with George. Would be nice, would be really great. He's a great speaker. It will be a great knowledge shared as well. Benchmark PID controller performance, and have you all a good week. Thank you.
Excellent. Thanks, Tim.
Thank you.
Woo!